Welcome to my video series on signal analysis basics. I am not a specialist in this. I am learning about signal analysis, and so I'm just trying to share the things that I'm learning about. As we go through this, I hope that I can share some of the things that I've learned about in such a way that you can be able to understand them for yourself. So first of all, we'll start off with how to represent signals mathematically. Well, the easiest way is to represent signals as vectors in a vector space. And the reason for that is that signals tend to be orthogonal to one another in frequency, in the frequency domain. Signals, in different domains tend to be orthogonal to each other. So, for example, a signal in time domain will be orthogonal to a signal in frequency domain. In this case, I'm talking only about audio signals, but it can easily be expanded to video signals, to radar, to other signals that we use in real life. So let's just jump into it. First of all, let's talk about how to do coordinate transformations. Like I was saying, signals tend to exist in different domains, and each domain is orthogonal to the other. We have to be able to go from one domain to another. So we should do it first in a way that's easy for us to understand. We're going to do it with vectors. We know how to do this, so just a little bit of recap. First of all, if we have a vector u that has a magnitude of ax in the x direction and magnitude of ay in the y direction, and we want it to be described in the v and w directions, very much like what we have in this graph over here. If I have a vector and I want to describe it not only in the x and y axes but also in the v and w axes, then I need to do some sort of coordinate transformation. So how would we go about doing that? Well, in this first case, we can multiply both sides by the basis vector, or in this case the unit vector of the magnitude that we want to find. So if you want to find the magnitude of AV in the v direction, then we multiply everything over here. We make these two functions equal to one another. These two vectors are equal to one another because that was the stipulation that we said at the beginning. And then we multiply both sides. We dot both sides with the v unit vector. And you know how this goes. If you have a unit vector v dotted with v and they're parallel, then this becomes 1. And if you have v and w and they're perpendicular, then those go to 0. These two, x and v, however, are not perpendicular or parallel. They have an angle in between them that is less or greater than 90, and is not equal to 0. And the same for y and v. It is not equal to 0, not equal to 90, not equal to 180, and not equal to 360, which is the same as 0. So, seeing as AW is now multiplied by 0, we can see that on one side we have the magnitude AV and we have a representation of what the magnitude AV looks like. And we can do the same for AW. Doing this allows us to give a representation of what our vector looks like in the v and w axes when transformed from the x and y axes. Now, we've talked about the angle in between them, and there is an easier transformation to make there that we use all the time. It's the transformation using cosines and sines. And you can see a of x, if you multiply the cosine of a of x, if you multiply a of x times x dot v, then you'll get a of x cosine theta, where theta is the angle between x and v, and so on and so forth. I have down here a matrix multiplication. In this case, this matrix inside is called the transformation matrix. It allows us to transform from the x and y axes to the v and w axes. So we can change these values x dot v and y dot v, x dot w and y dot w, to something that is much better known. Excuse me for a second. To something that is much better known. For example, we can change it to our cosines and sines. This is definitely much easier to see in terms of a diagram, how one can transform from one axis to the other. So continuing on from here, let's say that we change v and w to v1 and v2, and x and y to x1 and x2, just so that we can make things a little bit easier to see where we're going from. If we have everything on one set of axes with the same definition of the basis vector, and just numbers to differentiate between each axis, and then we can be able to have a better understanding of what's going on here. So after doing that, let's pull this up a little bit so we can work down some more. We can work downwards from there. If we do a little bit of work, if we say that v1 dot x1 is equal to v11, v2 dot x1 is equal to v21, v1 dot x2 is equal to v12, and v2 dot x2 is equal to v22, then we are able to get something that is something that we can put into an easier to understand form, like a summation, shown down here. If we want to find u, the vector u, then we can, or the magnitude of the vector u, then all we need to do is sum up all of the magnitudes of its vectors, or of its unit vectors, or its basis vectors, and that is done by multiplying each basis vector with a scalar multiplication. And that gives us our, I'm sorry, I missed out some vital information here. Yeah. So using this, we can be able to have a good representation of how to be able to transform a matrix. The most important part is this section down here, which allows us to find the magnitude of a vector along any axis. If we want to find it along, say, the second axis on the n side, and we know what all of the m axis looks like. So if we want to find the second axis in the n dimension, and we know what the m dimension looks like, this is how we would do it. We would find the sum over m of every basis vector that's multiplied with an m vector times its respective constant, and that would give us our actual constant for the n side. This ends the first part of signal analysis basics. I hope you can join in next time when we'll talk more about the inner product, something that looks like the dot product. Thank you.